Hey everyone, and welcome to this explainer. Today we're going on an absolute trip. We're starting right here in our own backyard and traveling all the way out to some of the most extreme, completely invisible physics known to humanity. So get ready, because we are going to explore the bizarre, the unseen, and the downright mind-bending stuff that defines our cosmos. So, here is our flight itinerary. We'll start in our cosmic backyard, exit the solar system, traverse a stellar graveyard, investigate black holes and their imposters, surf some ripples in space-time, and finally, look through our newest cosmic eyes. All right, Section 1, our cosmic backyard. We're kicking this journey off remarkably close to home because, honestly, our own planet still holds a few surprises. For instance, did you know Earth actually had a secret second moon? Seriously. Back in 2024, this tiny little space rock we call PT5 became our legitimate mini-moon. Just for 2 months, this fast-moving object dipped close enough to us that it got snagged by our gravity, hanging out in our night sky like a temporary companion. And that capture happens because of something called a Hill sphere. You can think of it like this giant, invisible gravity bubble stretching about 1 million miles out from Earth. When a fast-moving object, like PT5, wanders into this zone, our gravity can actually snatch it up for a bit before the sun eventually yanks it back. Moving just a bit further out into the neighborhood, we've got to say a bittersweet goodbye to NASA's MAVEN orbiter. After an amazing 11-year run, the spacecraft basically went silent after this mysterious spin ended up draining its batteries. But man, the legacy it left behind is huge. MAVEN showed us that Mars is literally losing about 100 grams of its atmosphere every single second to the solar wind. It's a process called sputtering, and solar storms make it so much worse. This was the exact smoking gun we needed to prove how Mars went from this warm, wet world capable of supporting water right into the completely dry, frozen desert it is today. Section 2. Exiting the solar system. Let's zoom way out to the very edge of our neighborhood and cross into the great unknown. For the longest time, scientists just kind of assumed that the solar wind quietly faded away the further out it went. But Voyager showed us that is not the case at all. It actually smashes into the interstellar plasma at this sharp, definitive boundary called the heliopause. It's quite literally a physical, bubble-like barrier separating our solar system from the rest of the galaxy. And speaking of bubbles, 1,000, that is the diameter, in light years, of the local bubble. It's this massive void our solar system is just drifting through right now. Computer simulations show this whole area was carved out millions of years ago by ancient supernovae going off and just sweeping all the interstellar gas outward like a cosmic snowplow. Moving right along to Section 3, the stellar graveyard. Once we exit that localized bubble, things get really weird really fast. We're entering a space filled with the ultra-dense corpses of ancient stars. Just take the number 43,000. That staggering figure is the RPM of one specific, absolutely wild pulsar. It is spinning over 700 times a second. That's faster than a jet turbine. And as it spins, its insane magnetic field acts like a cosmic lighthouse, sweeping these deadly beams of radiation across space with the precision of an atomic clock. Which brings us to Section 4, black holes and imposters. Now we're diving into the objects where gravity completely breaks our standard understanding of physics. So the thing about black holes is they're completely invisible. Gravity is so intense there that not even light can escape the event horizon. What telescopes actually pick up is the glowing, superheated accretion disk. It's just doomed matter swirling around the outside, kind of like Saturn's rings, but violently hot. But what if a black hole isn't a black hole at all? Modern astrophysics has thrown this wild theoretical curveball our way. What if some of these incredibly dense objects are actually cosmic imposters, just hiding completely different physics inside? Enter the gravistar. Physicists think this could be an object so dense it bends light exactly like a black hole. But it doesn't collapse into a singularity. Instead, its core is supposedly filled with vacuum energy. Yeah, the exact same dark energy that's pushing our universe apart. The real mind-bending difference here? The event horizon. A true black hole has a point of absolutely no return, but a gravistar? Technically, it doesn't. Because it lacks that horizon, information in light could theoretically escape its surface, which would honestly solve some massive headaches in modern physics. All right, Section 5, ripples in space-time. Let's look at what happens when these titans actually crash into each other. Whether they're true black holes or exotic gravastars, their collisions send literal ripples through the fabric of the universe. The LVK detector network is catching these crashes right now. I mean, look at this. They're finding black holes spinning at 40% the speed of light, and these weird lopsided mergers where one is double the mass of the other. These extremes are just blowing our previous models completely out of the water. And beyond those individual violent crashes, the nanograv team has picked up something even more profound, an overarching cosmic hum. It's a background noise caused by millions of supermassive black holes slowly dancing together all across the universe, just gently stretching and squeezing the space-time around us like ripples in a pond. Finally, Section 6, New Eyes on the Cosmos. To actually perceive this invisible, humming, twisting universe, humanity is deploying some revolutionary new tools. Take the James Webb Space Telescope. It recently found a dormant supermassive black hole from just 700 million years after the Big Bang. But the absolute shocker is this 1-to-1 mass ratio. The black hole is roughly equal in mass to the stars in its surrounding galaxy. Down here in our local universe, that ratio is usually more like 1 to 1,000. This discovery is fundamentally rewriting how we think galaxies form. Meanwhile, we've got the Vera C. Rubin Observatory gearing up in Chile. Think of it like a live-action sports photographer for the cosmos. By imaging the entire visible southern sky every few days, it's going to map out dark matter, track dark energy, catch live supernovas, and even spot kilonovae, which are neutron star collisions that literally forge the universe's gold. And these same revolutionary tools are desperately trying to settle a massive debate called the Hubble tension. Basically, different ways of measuring how fast the universe is expanding are giving us totally conflicting numbers. Physicists are really hoping these unprecedented new observations finally force the math to make sense. So I want to leave you with this final thought. As we open up these amazing new eyes on the cosmos, from Webb to the Rubin Observatory, are we finally going to solve the Hubble tension and tie up the loose ends of physics? Or are we just scratching the surface of entirely new, terrifyingly beautiful mysteries? Let that sink in. Thanks for joining me on this explainer, and keep looking up.